Today we're going to talk about the graph of the derivative. What we're actually going to do during the course of these notes is be given different functions, the graphs of different functions, and we're actually going to sketch graphs of their derivatives. Okay, so as we think about graphing or sketching the graph of a derivative of a function, I want us to remember it's all about the slope. That as we are thinking about graphing that derivative, we're thinking about analyzing and taking a look at the slope of the tangent lines at various different x values on the original graph. So if we kind of take a look at that thought, okay, so if I want to look at different tangent lines that I could draw in that intersect this graph at one place as I go through. So just looking at that first little hill, okay, on the left-hand side here, you can see that I have, as I look at these tangent lines, that they are in fact positive slopes. They are increasing, okay? I'm going up from left to right until all of a sudden I get up here. And then at what we would call our relative maximum, if you remember from pre-calc last year, our slope is actually a horizontal line. And remember, when our slope is a horizontal line, the slope of that is actually 0. So when we have a horizontal line, we have a slope of 0. And then after that, we start decreasing and we start going downhill until we get to a relative min. And once again, we are going to have another horizontal tangent. And so we'll have another slope of 0, and then we'll start increasing again. And what you'll start noticing is that the closer you are to those horizontal tangents, the more your graph is kind of more shallow here. So, not all of them are drawn in, but as we look at these horizontal tangents that get closer and closer to the relative max here, we can see that at this value right here, we have a more shallow slope than we did down here. And same thing here, if we talk about the the slope of this line compared to the slope of this line, it is more shallow. And so this is all going to be important elements and important factors as we graph that derivative. All right, so let's summarize a couple of the things that we talked about right here. So first of all, we said that if the graph of the original function was increasing as it was right here and right here, okay, so when the function was increasing, we said that those slopes, those green tangent lines, were positive. Okay? As the graph of the function leveled out, in other words, when it hit a relative min or max. So when it changed from increasing to decreasing, we said that the slope was 0. And as the slope was decreasing, as the graph of the function was decreasing, then we said our slope was negative. And that would be like here, this middle part of the graph, when it's going downhill. In between our relative max and our relative min, it goes downhill, and those slopes, those horizontal tangents, the slopes of those horizontal tangents were negative. Okay, so what does this mean for the graph of f prime, for the graph of the derivative? Well, keep in mind that the slope is the derivative. That's the f prime. So if you are graphing a positive number, well, then on the graph, how would that show up? It would be above the x-axis. And if it's 0, well, that would be on the x-axis. That would be an x-intercept. And if the number is a negative number, then on the graph you would plot points below the x-axis. Okay, I just added a sentence, and I want you to actually think about it. Get it down in your notebook, but let's also think about it. It says, the steeper the slopes are. Okay, the steeper the slopes are. So we talked about up here that here was much more steep of a slope than as we were kind of flattening out over here. Well, if you think back to Algebra 1, the steeper your slope are, well, you know, if we're talking about a line with a slope of 3, that's going to be much steeper than a line with a slope of 1/3. So the steeper the slope is, the larger the number of that slope is. And so then the further it will be from the x-axis, because you're plotting a number that's further from 0. So that's all that's saying. We're going to go ahead and practice actually graphing the derivative a few times, and I think as we go through it more, it's going to make more and more sense, so stick with me. Okay, so we're going to take a look at our first graph here, and if you want to go ahead and make the best sketch that you can of f of x, okay, and then you can see I have a couple other things set up for myself. On the left hand underneath the graph, I have this number line, and basically what this is I take the x-axis here and I make myself a number line underneath, and so I can interpret the slopes like we talked about in the table just a second ago. And then over here I have the an axis set up ready for my f prime of x. Okay, so the first thing I want to do is really get a picture for those relative max and mins. Those are going to be crucial values because that's where we're going to have our horizontal tangents. So we can see here that we are going to have horizontal tangents. In other words, slopes of 0 right in between -2 and -3, and just to the left of the y-axis there, so just before 0. And so what I'm going to do is over here on my number line, I'm going to go ahead and mark those as zeros. Okay, so on my number line, I'm going to go ahead and put a 0 right here between -2 and 3, and also right to the left of 0. Okay, so that's where my slopes are 0. Now, in between and before and after those zeros, I have either positive or negative slopes. And so I want to go and look at my original function. Was the graph increasing up until my x value of, let's just say, -2.3, or was it decreasing? Well, you can see here that these slopes are, in fact, very positive. Okay? And so we would say that this was positive. In between my relative max and my relative min, what's happening? Well, my slopes are definitely going downhill. And so we would say that they are negative. And then after that relative min, I start going positive once again. And so positive. All right, what that's going to tell us over here on f prime? Well, right away, I'm going to go ahead and mark in my zeros. And my zeros mean, if you remember, when it was a relative max or min, you are on your x-axis, okay, because the slope is 0. And this is the graph of the slope. So I'm going to fill in for myself -1, 2, 3, 4, and then over here +1 and +2. So I can go ahead and fill in that between -2 and -3, and then right here. So those are my zeros. Now what I know is that because I have a plus sign, a positive here to the left of -2, okay, that means that my graph is going to have to the left of this 0, right here, that means that the graph is going to have to be above the x-axis. But how's it going to look, okay? We know it's up here someplace, but how's it going to look? Well, remember we talked about the steeper the line, the further it is from the x-axis. So you can just kind of guesstimate, okay? You can see here that this is a very steep slope down here. And so maybe this is a slope, you know, you could actually kind of calculate it, but maybe this is a slope of +3 or +5. And then it starts to get a little bit less and a little bit less, and then it starts to level off, okay? And so what we're noticing here is that our slopes are getting closer and closer to the x-axis until over here where we actually kind of flatten out. So these slopes are very large, and so they come from up here and then they come down and they get smaller and smaller. They get less and less steep until you hit your relative max. Now what happens? Well, on this side, they are all negative slopes, so they're all going to be below the x-axis, okay? And so what happens though, again, now we start off pretty shallow, and then we get steeper and steeper until we get shallow again. And so you can see here we are close to the x-axis, getting further away, but then starting to come back to the x-axis based upon the size of those slopes. So here we are close to the x-axis, getting further away, and then coming back towards that x-axis. Okay, remember that the further you are away from the x-axis, the steeper it is. And then what's happening over here? Well, once again, we are pretty shallow to start off, so our slopes are pretty small, so they will be close to the x-axis, and then they get steeper and steeper, and so further away. And so we can see we'll have a graph like this. So that is the graph of our f prime of x. Okay, now does it make sense that if you look at our original function was a cubic, okay? And so does it make sense that the graph of the derivative would be a x squared graph, a quadratic? Absolutely. We know that when we take the derivative of x cubed, we get 3x squared. And so in fact, it does make sense that the derivative of a cubic will end up being a quadratic. And we want to keep that in mind just for test-taking elimination strategies. Okay, so taking a look at our second function here, g of x. All right, again, get a good sketch down of g of x, and then we're going to start to analyze it. Okay, so once again, the first thing I look for are my relative mins and max, because I know at the relative mins and max I'm going to have horizontal tangent, meaning that I'll have slopes of 0. And so I can see right at about -2 I'm going to have a slope of 0, to the right after 0, so right there, and then right at about at 3 I'm going to have a slope of 0. Okay, and then we're going to go ahead and start analyzing the slopes. So you can see to the left of -2, so I'm talking about this area right here, is the graph of g of x increasing or decreasing? It is definitely increasing from left to right, which means that the slopes, as I look at them, are going to be positive. They're going to be also going up, so positive. Then if I look in between my next pair of relative mins and max, okay, so my next pair of zeros, here the graph is doing what? Well, it's going down, it's decreasing. If it's decreasing, that means that the slopes are going to be negative. So I'm going to put a negative sign here. Okay, in between my next pair of zeros, what's the graph doing? It is going up, it's increasing again, so again I'm going to be putting a plus sign. And the last one is after my last relative max, I'm going to be going again down, decreasing, and so my slopes are negative. Okay, so on my actual sketch over here of g prime of x, I'm going to go ahead and mark my zeros. My zeros are where the graph is going to intersect the x-axis. Okay, so I'm going to be at -2, just after 0, and at 3. Okay, so those are the places I'm going to be on the x-axis. All right, now, if I look at my slopes, okay, so I'm going to go ahead and sketch those in. So here are my slopes. You can see that's a pretty steep line, but then you can see it gets more shallow, more shallow, more shallow. And so you can see here, maybe that this slope is a positive, say +2, +3. And then it's going to flatten out. So maybe this was a positive, if this was a +3, we can say this one was a +2. And then maybe this is a +1.5. And this looks like maybe a half or a quarter. Okay? And so as I am looking at that, all right, I can plot those points. So we said here, this slope here was a +3. So over here, I'm up here. And then we are getting a smaller slope, maybe a +2. So we're going to go here. Okay, and then this one was maybe a slope of 1.5, so we can go here. And you can see what's happening is that these slopes, okay, here we are at a fraction, so we're down here real close. And so we have this downward, okay, they are all above the x-axis, but they're decreasing in steepness. So therefore, they're getting closer and closer to the x-axis. All right, now looking at the next set. So again, we start off real shallow and negative, so it's a very small negative number. Okay, and then they get steeper, and then they start to shallow out again. So we've seen this before. Okay, they're going to be close to the x-axis, but below the x-axis because they're negative, and then it turns around and comes back up. Okay, so you can see right at about -1 was when you were at your steepest. And so that's why at -1, that's where it's furthest from the x-axis on my g prime of x graph here. Okay, now we're going to go back the other way. And again, now we have a positive slope, so we're going to be above the x-axis. And same thing, start off really shallow, and then we get steeper, and then we level out again. So it looks like maybe, but it's not, we're not getting real huge on any of these. So, we start off with a fraction, maybe a 1/2, a 1/4, and then we get up to maybe about just a slope of 1 or 2, and then we start leveling off again. And so same thing here. We're going up, and then we're coming back down. Okay? And then lastly, same thing. We are starting off shallow, and again we get really steep. So we're going to go, just continue down. Okay, and we started off again with our g of x. This was a quartic graph, and we end up with a cubic. And again, that makes sense because we're going to decrease the power by 1, because when we take the derivative of a quartic, we end up with a cubic. Okay, good job. Okay, there are 3 different situations when a function is not differentiable at a given x. And this matters because when we are graphing the derivative of a function, if it's not differentiable at that value, it's going to affect the graph of the derivative. And so we want to talk about these just really briefly. The first is called a corner. Okay, if your graph comes to a corner, okay, to a 90-degree angle, a sharp turn, that would be a time when it is not differentiable at that given x value. Okay, you cannot draw a slope. Okay, you can't find the slope right at that corner. All right, the second thing is if your graph actually comes to a vertical line. So if you look here, this graph, it's kind of level, and then all of a sudden it gets really steep, and right here it comes to a vertical line, and so we call that a vertical tangent. And so the second time you would not be differentiable is if there is a vertical tangent in your graph. Okay, because we know if we were to graph the tangent lines here, if I'm graphing this tangent line right here, okay, it's going to be a vertical line, and we know the slope of a vertical line is undefined. Therefore, it can't be differentiable. Okay, the last one is if there is a discontinuity in your graph. And this should make sense because if there's a discontinuity, it means that the limit might exist from the left and from the right, but the limit doesn't exist at that value. And so then you can't take the derivative at that value. Okay, so there are the 3 things that you just kind of want to keep in mind, and we're going to see how that affects the graph of the derivative coming up. Okay, next up here we have h of x, which is an absolute value graph. And what do we know about absolute value graphs? We know that they are really just 2 lines kind of coming together and intersecting at this point, okay? And so what we know is that this here on the left-hand side, we can definitely tell that that is a slope, and there's no reason to draw in horizontal tangents. We can tell that the slope of this line is in fact -1, that all the way along that our slope is -1. And we can tell on this part of the graph, okay, so this, our slope was -1. And over here on this part of the graph, on the right-hand side, we can tell that our slope is in fact +1, rise over 1 over 1, 1 over 1. And so we can say that for this whole part of the graph, our slope is equal to 1. And then we just talked about that you can tell where those 2 slopes intersect, we are coming at a corner. And that corner at x equals -2, the graph is not differentiable. Therefore, we are not going to be able to graph a value at x equals -2 on our graph of the derivative. Okay, so what we do know, however, is that we have these slopes of +1 and of -1. And we can see that the place where that changes is at -2. And so up until, on the graph, up until an x value of -2, I have a slope of -1. So I have a straight line, and then at -2 I have an open circle. Okay? Then, after every x value after -2, I have a slope of 1. And so I can draw in that line. but at x equals negative 2, it does not have a value. Okay, so this is the graph of our derivative of h of x. Okay, and if we analyze this just for a quick second, you can, just again, pick it apart. Up until the x value of negative 2, the slope was negative 1. And this makes sense because this was, h of x was a line, and the derivative of a line is just a constant. The derivative of a linear function is just a constant. And so when we graph a constant, what do we get? We get a horizontal line. Up until the corner here, where we said that the derivative does not exist, and then here we have another line, a line with a slope of 1, and so we are graphing that in. So that's all there is to it. All right, let's go ahead and do our last one. Okay, this next graph illustrates another example of our example of when a graph is not differentiable at a certain value. And here again, it's at x equals 2, x equals positive 2. We say the graph is not differentiable. And this time it's because it's a vertical tangent. If I were to sketch in my tangent lines here, okay, going along, you can see, and then all of a sudden I have this vertical line here, a vertical tangent. And so we know that the slope of a vertical line is in fact undefined. So at x equals 2 on my graph, I'm actually going to draw it in as a undefined vertical line. Okay, so in other words, a vertical asymptote at x equals 2 on my graph of the derivative. Sorry, this should be labeled j prime of x. Okay, now what's going on with the slopes? Well, as we look at the left-hand side of that x equals 2, what's happening? Well, this time it's a little bit different than some of the polynomial functions we had. Okay, here we actually are starting out pretty shallow. Okay, they are increasing, so it is positive. So we know we're going to be up here in the graph someplace. We know we're going to be above the x-axis, okay, because these are all positive slopes. So, but when we look here, this at like right before the right before the y-axis, maybe on the y-axis. Okay, what's that slope? It looks like maybe it's a fraction, like positive 1/4. Okay, and then we start getting a little bit higher, and then we all of a sudden we get extremely steep. And so what's happening here is here we are very close to the x-axis because we have these very small fraction slopes. And then as we get closer and closer, we start getting much larger. And so if we take a look at this, we have a graph that looks like this. Okay? And so, because again, down here, our slopes were very small. Our tangent lines were not at all steep, therefore producing very small slopes, and so they are going to remain close to the x-axis. Then, as we get closer and closer to that vertical tangent, our slopes get steeper and steeper, and so that's why we get further away from the x-axis. Okay, now if we look at what's going on after x equals 2, well, for a second, is j of x increasing or decreasing here after x equals 2? And if we notice, it's still increasing. Okay, and so we are going to have slopes, again, we're going to have values above the x-axis after the vertical asymptote. And that's important that we don't always have to have a negative slope. Everywhere on j of x, we are increasing. We are always increasing. Not at a constant rate of change, clearly, but we are always increasing. And so here, what's happening? Well, again, right close to that x equals 2, we have extremely steep slopes, but then they get more and more shallow. So on the other side here, we're going to start off very far away from the x-axis, but then we're going to get closer and closer. And so we end up with a graph that looks like that. Okay, gang, so I'm just going to finish off with a really fast one here. If we're given this function, f of x, it's a quadratic, I just want to summarize these rules for you and make sure that you fully understand. Okay, so if you look at your graph and if you think back to the table we started with, here on the left-hand side, up until when x equals a, we have an increasing function. What does that mean? It means that we are going to have positive slopes. At x equals a, that's where we have a horizontal tangent. What does that mean? That means that we're going to have a derivative of 0. I'm going to put that right on. That's where it intersects the x-axis. And then after that point, what happens? Well, we have a decreasing function, meaning we're going to have slopes that are negative. So slopes that were positive before A, and again, they start off pretty steep, and then they get more and more shallow. And so they're going to start off further away from the x-axis and then get closer and closer to the x-axis. Positive. Okay, then as we move past A, now we have negative slopes, so that means I'm going to go below the x-axis, and again, they get more and more steep, so further and further away from the x-axis. Okay, make sure you go through these notes, make sure you have this concept understood to the best of your ability before you come in, and we're going to practice graphing a bunch of derivatives in class next time. Thanks a lot, guys.